All right, here we are in 2.7 applications of the cross product. Okay, so before you proceed here, please make sure you have worked through 2.6 and you're familiar with what the cross product is, what it means, and how to calculate it. Okay, otherwise you will just get confused. So make sure you do 2.6 and understand it before you come into 2.7. All right, so the first application, there are three. I'm going to do them all in one video. The first application is directly from the definition of the cross product, actually, and that is to find the area of parallelograms and triangles in the three-space coordinate plane. So you can see here, all right, that when we talked about the cross product originally, okay, we defined the magnitude of the cross product as the area of the parallelogram that is formed by the two vectors coming together tail to tail, okay? So the very first example that we will do is just exactly this example. All right, so I've been given a parallelogram. Notice I have not been given the vectors. Instead, I've been given the vertices, okay? And I provided you with a parallelogram labeled with the vertices to show you their orientation to each other, okay? It's really important when you do this that you're selecting two vertices that come together at one of these, you're selecting two vectors that come together at one of these vertices, okay? So I could pick the vectors that come together at, from tail to tail, SP, SR. Or I could pick the vectors that come together at R, so RQ, RS. Any of the four corners, you could pick the vectors kind of emanating from those four corners, and you will get the same answer, okay? Because it's scalar, all right, that we're calculating the magnitude. So for my purposes, I am going to use the vectors kind of coming out of vertice S. You can pick another pair and check in that you get the same answer. Would be a good sort of variation on this. All right. So notice, because I am using only these two sides essentially of the parallelogram, okay, I'm not actually even going to need to use vertex Q in my calculation. I'm going to be finding the cross product of SP, okay, remember tail to tail, so SP and SR. Okay, and remember, we have to find the individual vectors, then we have to calculate their cross product, and then in the end, we have to find their magnitude. Okay, so there are quite a few steps here. So the first thing I'm going to ask you to do is to just find the vectors SP and SR. So I will pause for a moment. You can do the same. Okay, so here I've calculated SP and SR. Okay, remember we do P coordinates minus the S coordinates. So 3 minus 2, -1 minus 6, and a 1 minus 2, etc. Okay, I'm not going to go through all of that. So the next step would be to calculate the cross product of these. And remember, when you're writing out the list of numbers for your calculation, you always start with the Y coordinate, and then Z, X, and then come back and do the Y again. All right, so I'm going to leave you to work on that. Okay, so I've come back. I've written out my coordinates in the order that I need to do and to do my calculation. So now I'm just going to calculate the cross product. So remember, we do -7 times 2, -14, minus a -9. Okay, so that's going to be -5. Then we have 6 minus 10, so that will be -4. And finally, we will have -15 plus, because it's minus a minus, so negative 15 plus 14. So that will give me minus 1. So in blue, this is my cross product. So if I was just calculating my cross product, I would be done. But I'm calculating the magnitude of my cross product. Okay, so I'm just going to quickly do this. And just use our extended Pythagorean theorem. Okay, this would be 25, 16, and 1. Okay, so I'm going to add all those together, and I'm going to get the square root of 42. All right, you could leave it like that, but I'm going to put it into a whole number to one decimal, so it's going to be 6.5. And then don't forget your units, okay? The units are going to be square units, or you can write units square, okay? Because we're talking about area, right? So just make sure you're good with that. Again, you could have selected another pair of adjacent sides, vertices, but you'll get the same answer. Okay, so the next thing here is the area of a triangle. And if you think of the area of a triangle, if you're looking at a parallelogram, okay, if you think about cutting the parallelogram in half like this, you would get a triangle. So in this case, if I'm given a triangle, basically what I can do is I can find the area of the parallelogram defined by kind of that triangle, and I can divide it by 2. So I'm just going to pause. I'm going to draw a quick diagram over here, and you can do the same. All right. The placement of the vertices relative to each other doesn't matter, but I'm going to place them G, H, and I. Okay, so you can see here I've drawn my triangle. All right, so if I take this side HG and I kind of move it over and draw a parallel side there, and then I take the side HI and I draw a parallel side up here, you can see we've created a parallelogram. And you can see that the triangle defined by GHI is half of that parallelogram. So I am actually going to use my cross product to find the area of the parallelogram. And then what I will do is I will divide that in 2, and that will give me the area of the triangle. Okay, so I'm going to put on pause. So you're going to want to find HG, HI, do the same process we did above, but the very last step will be that your final calculation, you will divide it by 2. Okay? Okay, so you can see here, I identified vector HG as negative 2, 3, 1, and vector HI as negative 2, 4, 3. Okay, then over here, I put together my calculation for the cross product of these two vectors. Okay, so check your work. I'm going to now calculate the cross product, find its magnitude, and then finally divide it by 2. So you can pause here and do that. Okay, so now I'm back and I calculated the cross product. Okay, so when I calculated the cross product, I got 5, 4, negative 2. And remember, we're dividing this by 2 in order to identify the area of the triangle. So I find the magnitude of the cross product. Okay, following these calculations, I got the square root of 45. I divided by 2. So I'm going to just give an approximation here, but this is going to be approximately 3.4 square units. Okay, so review over that, and we're going to move on to the next application. All right, so the next application is, instead of finding the area of a flat kind of planar shape, we're going to be finding the volume of a three-dimensional shape. And this is probably a shape you have never heard of. Maybe you've seen before, but you've never called it anything. And this is called a parallelepiped. Okay? Parallelepiped, right? So really the whole idea about a parallelepiped is that it is essentially a three-dimensional parallelogram. Okay? You can see here, I have my opposite faces on either kind of front, back, side to side, top, bottom. Okay, any of those opposite pairs are parallel planes to each other, and they're congruent parallelograms. Okay, so whenever I am dealing with the volume, sort of the general formula for the volume of a three-dimensional shape is to find the area of the base of the three-dimensional shape, and then you multiply that by the height. Okay, so let's just take a look over here at what we have. We have our parallelepiped is identified by three vectors, all coming from this same bottom corner. Okay, I have vector A, vector C, and vector B. You could do this in different orientations, but for our purposes, I'm going to take, okay, that area of the bottom, okay, of the parallelepiped, and that's what I'm going to take as my area of the base. So for this, we can simply use what we did above, which is that we will find the magnitude of our cross product of angle of vector B times vector C, cross product. All right. You could do C cross B because we're dealing with magnitude here. Okay. I'm not worried about any direction element. Okay. And then what we would do, I want to just draw an extension to this. All right. We need the height. Okay. So we're going to use this cross product in a different way as well, okay? So I'm going to use the cross product of B and C. First, I'm going to use it to find the area of that bottom, okay? And then I'm going to use it, not its magnitude. I'm going to use its vector, okay? So if I find the vector cross product, okay, of C cross B or B cross C, okay, in this case I'm doing B cross C, if I think about my left-hand rule, okay, and that actually will be the vector on which we will project and find the height, okay? So remember, the height of a three-dimensional shape is going to be perpendicular to its base. That's how we find and define the height, okay? So we've used the magnitude of the cross product to find the area of the base. Now we are going to use the actual cross product, okay? And we are going to project the third vector, vector A, onto that cross product. Okay, I know this is a bit of a mishmash of all the different things that we've done. Okay, so remember, the projection of A onto B cross C, which is this vector. Okay, that's like the shadow of vector A on B cross C. That will give me that height, distance, okay? I'll use the scalar of the projection. I do not need to worry about the vector. It would, we're doing a calculation here with scalar units, okay? So here, I'm going to use a big star for my multiplication. Because if I use a cross, it looks like a cross product. If I use a dot, it looks like a dot product. So please let this big asterisk, big star, represent multiplication, okay? So remember when we're finding the projection of the scalar projection, say, of vector u onto vector v, all right? You can look back on this, okay, in the applications of the dot product, all right? What we're going to do is we're going to get the dot product of the two vectors. So in this case, it will be A dot B cross C. And then I will divide that by the magnitude of the vector being projected upon, okay? So here, what I need to calculate is I need to calculate the projection of my vector A onto B cross C. Okay. So I'm going to have my magnitude of B cross C. All right. Then I'm going to use this formula over here. So I'm going to have A dot B cross C. Okay, this is my U vector. This is my V vector being projected on. All over the magnitude of my V, which in this case is B cross C. Excuse me, I drew these brackets wrong. These brackets belong in the top only. Okay, so you can see here, I can cross these out. They will cancel. And I'm going to be left with the magnitude of A dot B cross C. And you're probably thinking, that already is going to be a scalar because whenever I take the dot product, it is a scalar. But in this case, where the magnitude will come in useful is we need this to be a positive value, okay? We would never have a negative volume. So depending where your cross product ends up, whether you're dealing with the opposite variation, okay? When I get my volume calculated, I might end up with a negative scalar from the dot product. So when I'm taking my final magnitude, what I'm actually doing is I'm taking my absolute value of whatever the scalar is that comes out of this volume formula. Okay? All right. So I'm going to pause here. Just review this. Make sure it makes sense. Okay? I can go over it in class if need be. But watch this a couple times if you weren't sure. Okay, I've taken a moment to set this up and draw a not quite complete diagram, but enough of a diagram for you to recognize what's happening. So here in example 3, we want to find the volume of the parallelepiped with the sides determined by these vectors, u, v, and w. Okay? I have chosen to orient it this way. Okay? So remember when we were calculating this, we were using the area of the base, and then we were multiplying it by the projection of u onto the cross product of v and w. and we came up with a simplified formula to use. So the first thing we're going to do is we're going to calculate the cross product of V and W, and then we will simply achieve this whole thing just by taking the dot product of U with the cross product of V and W, and then taking its absolute value. Okay, so I'm just going to fill this in, and then I'm going to leave you to do some calculations. So I have 2, -6, 2 for my U, my V, 0, 4, -2, 2, 2, -4. Okay, so remember, when we're doing this, kind of like an order of operations, we do our cross product first, and then we apply the dot product after. Okay, so when I calculate my cross product, I'm going to want to start with those y values. Okay, so I've come back, I've calculated my cross product. All right, I wrote my work up here. Okay, and when I calculated my cross product between V and W, I got -12, -4, and -8. Okay, so check your work there. So my final step is that I'm going to find the dot product. Okay, so remember, I'm just going to multiply the corresponding coordinates and add them together. So I'm going to have -24, -6 times -4 will be +24. Okay, and finally I will have -16. Okay, if you see this, you can see these cross out. Then I'm going to have the absolute value of -16, which is going to be 16. And remember, we're doing volume, so this is going to be in cubic units. Okay, as opposed to an area where we have square units. Okay, so this is that last step that I was talking about. We would never have a volume that was negative. So we need to make sure if we do our dot product and we get a negative value, that last step is the absolute value of whatever the dot product is. So in this case, it will be +16. Okay, so this is the same, except now I've been given points in space. All right, so what makes this easier for us is that my A, which is where they all start, this is the origin. Okay, so it will be really easy to know the vectors because these are just going to be position vectors. Okay. All right. So what I want you guys to do is I just want you to determine the volume of this. Okay. I personally, I'm going to take the cross product of AC and AB, and then I'm going to find the dot product of that with AD. So this is the variation that I am using. You might choose to use a different one. Okay. But this is the variation that I will use. So you can pause and come back. Whether you're using mine or another, you should get the same final answer. Okay, I'm back and I completed the step of my cross product. So notice I just filled in with the position vectors. Again, you might have chosen a different configuration, okay? But at the end, you will get the same volume. All right, so I calculated my cross product, AC cross AB. I got 9, -3, 5, okay? And then the last step is to do my dot product. So I'm going to have -27, and then these will both be 0. So +0, +0, okay? So I have this situation again where I have a negative inside my absolute value sign. So I have to take the positive version, so my volume here would be 27 cubic units. Okay. Phew, almost there. All right. So one final application, and this is really exactly like example number 4, except here we are going to be working from points that are not centered on the origin. Okay, so you can see here I have my point D, all right, then I have E, F, and G. And so what this does, it's a test of coplanarity of 4 points in space. So remember we did that application in 2.6 where we were testing the coplanarity of 3 vectors. So we're just doing that same thing, but instead of starting from the vector definitions, we're starting from the points that define the vectors, and then we are going through the same steps from there, okay? So above, I did the dot product to the cross product, but then I took the magnitude of it to get the volume, okay? So here, actually, you'll see it's very similar, but you can imagine if all of these points, all of these vectors are coplanar, their height would be 0, okay? So if you think about volume as an area times a height, if my points and therefore my vectors are coplanar, okay, you can imagine that the volume would be 0. And that ties into what we were saying before, which is if we found the dot product and the cross product and they came out as a 0, it would mean they were coplanar. And that's because they basically create a parallelogram or a parallelepiped, that has no height. Okay, it's just a flat surface. So if I get a 0 here, it does mean they are in the same plane, all 4 points. Okay, so let's see if I'm going to get a 0 here, and if so, that tells me that I have a very flat parallelepiped, like no height whatsoever, and therefore they're in the same plane. Okay, so I'm just going to pause here. I want you to do the calculation and see what happens. Okay, I'm just popping in to say that what I'm going to do is I'm going to identify the vectors df and de to begin with, and then I'm going to find the cross product of those 2 vectors. All right, and then I'm going to take the dot product of dg vector with the cross product and see what I get. All right. Okay, I've come back and I identified vectors df and de. All right. Then I did my calculation over here to find their cross product. So we have a vector here as the cross product, 2, -8, -4. All right. So now what I'm going to do is I am going to identify vector dg. All right. So 3 minus 1 is 2. 1 minus 1 is 0. 3 minus 2 is 1. Okay. So that's my vector dg. And then I'm going to do the cross product from here. I'm going to take that cross product and find the dot product of vector dg with this cross product of vector df and vector de. Okay, so this is where I'm essentially calculating the volume. Okay, you'll recognize it's the same formula up above, except I have not taken the absolute value, but otherwise it's the same. Okay, so when I've worked on the volume before, I've gotten a value that is not 0 because I have a 3-dimensional figure that does have a volume in 3 space. The idea here is if this is going to be 0, it means my parallelepiped is flat, all like someone stepped on it, that has no volume whatsoever, which means all 4 of these vertices, all 3 of these vectors are flat on the same surface. So let's see what happens, okay? So I have 2 times 2 is 4, then I'm going to have 0, and then I'm going to have minus 4, okay? So I am ending up with 0, okay? Which means that these 2 vectors, okay, the cross product of DF and DE, which is perpendicular to both DF and DE, okay, when I find the dot product of that with vector DG, I'm finding that they are perpendicular. Okay, so tomorrow we're going to talk about that coplanar rule again, but we can think about it in 2 ways. We can think about the fact that then this tells me that DG is in fact coplanar with both DF and DE, or you can think about it as a parallelepiped that has a volume of 0 because it's completely flat. There's no height, all right? It's just those 3 vectors flat on a single surface. So the question is, do they lie in the same plane? The answer is yes. Okay, thank you.